All right, everyone. Thank you, everyone, for coming to this. I wouldn't say seminar, but it's a webinar. And in fact, the last seminar, this seminar has attracted quite a good turnout. I think that's due to the caliber of the speakers. Previously, it was Professor Relics, and now it's Professor Dawood Kothawala. And Professor Kothawala has been visiting us now for a month. And earlier on, he gave a series of very stimulating lectures at our workshop in the week. Some of the delegates here, and he spoke on reconstructing space and time. This went down well, and I think he will continue similar lines here. I should just point out to you something about Professor Kothawala. He completed his PhD at the Inter-University Center for Astronomy and Astrophysics, safe to say, the world leading center in that area of research. And he was supervised by Professor Tanu Patmanab, who was a really big name in gravity. I think he finished in 2010. Yes. 2010. And in 2012, he was appointed to the full-time academic post of the IIT, Indian Institute of Technology, Madras, which is Chennai. The name of the institution is Madras. And he's now full professor. He has many interests in general relativity, black holes, quantum field theory, and other areas. And it's always really interacting. Just in the fact, the first thing it's point out that I actually met you when you were still a student. But I think you were focusing on the senior students. Yes. Interesting. In 1997, we left some colleagues at Nagpur, and then we drove from Nagpur to Ayuga, which was for a week. It's very gentle drive, and I think that's right, we were part of that group. And we drove through a state called Taravati. And I've learned that that's where yes. Over to you.
So, again, just like, okay. So, let me begin by thanking Sunil for the very nice introduction and also for being a wonderful host. It's my first time in Durban, and it has been excellent so far, and I'm looking forward to visit next time as well. Like Sunil said, and Shubharti emphasized at the beginning, there is a relics in the title of the talk. So I will want to begin the talk by giving you a flavor of what one can expect. What do I mean by relics of a quantum space-time? And I hope that as we proceed, things will become clearer as to what I mean by relics. Like Sunil said, I also gave a set of 4 lectures in Drakensberg. For those of you who were present in the lecture, this should also put everything that was discussed here in a nice, broader context. But as you would remember, we will also be starting the other way as compared to the lectures we followed in Drakensberg. So let me begin. So this is the plan of the talk. I understand that some of the members in the audience are undergraduate students, so I'll start by discussing what we do know about space-time and gravity in a very basic manner, and we'll see how actually questioning those basic principles of gravity as the geometry of space-time can actually yield in itself some very important insights into the quantum structure of space-time. I'll then describe what I would like to call as the mesoscopic domain of space-time. I'll explain as we go along what I mean by mesoscopic, but this is the domain of space and time which is not quite classical, but it's not also fully quantum gravitation. It's somewhere in between, and the things will become clearer in a more robust manner as we go along. And I would try to indicate to you right in the beginning of the talk that our studies so far over the last 70, 80 years have given us two very robust clues into the nature of quantum space. Those two clues come from what is called as semi-classical gravity. I will describe those clues, but the clues are actually very easy to convey. The derivation is still rooted in debates and discussions, but they are very easy to communicate. So I'll discuss those two clues. And then I go on to a rather basic question of how you actually probe the space-time geometry. So when you want to probe something, you use a detector, set it in motion, and depending on the output or the behavior of the detector, you can probably say something about the nature of space and time in which the detector is moving. And there are two features of the detectors which you naively expect to come into picture in this case. One is the kinematical aspects of the detector, its acceleration, velocity, all those things that you can control. And the second thing are the details of the background geometry, because that determines how much force you have to apply, for example, to move a detector with a given acceleration. It depends on whether you are in a flat space-time or in a curved space-time. And we'll see how that affects the responses of detectors. And finally, I would try to combine point 2 and 3 here into a sort of formalism where you are trying to understand the nature of quantum space-time, space-time at very, very small scales in terms of quantities that your detectors can measure. So that is the plan of the talk. And before I go to the main bulk, I would just like to mention a story very wonderfully put forward by Michael Bell. And the story, I usually indicate this to indicate the nature of what I call as singular limits, which is what is going to give rise to some interesting results at the end of this talk. So the story which Berry says to demonstrate singular limits in mathematics, but we'll see how it applies in this, is that suppose you are eating an apple and you find a worm in the apple. It's very unpleasant, right? If you find a full worm, it's worse. If you find half a worm, you can feel slightly better, but not much better because you've already eaten half of it in the first part. And if you find very less piece of the worm in the apple after your first one, you've eaten most of it, even more disgusting, I must say. But if you don't, you take a limit of this process and you don't find a worm at all in the apple after your first bite, this limiting process will lead you to conclude that you've eaten a worm. It's of course ridiculous because there might not have been any worm at all in the apple in the first place. So this is an example of what is called as a singular limit. And I'll see that something very similar happens in quantum space. You do all this semi-classical analysis, get all the clues from semi-classical gravity, and you say that there is a scale beyond which we cannot make measurements in space and time. I will indicate all those arguments. That is something called as a Planck length, which I'll come to. But the basic question we are trying to ask is there any observable imprint of Planck length that is hanging around that your current observations are not able to explain? They are still there. But these are really relics of a quantum space. That explains the term relics in the title. We'll see that it arises precisely because of a limit like this. You may not see a Planck length or a small space in your description of the space. But the very fact that such a limit exists can make a drastic difference to how you describe the space-time geometry. So I hope that we'll come to that part comfortably before the end of the Now, as promised, I'll first begin to describe by what I mean by mesoscopic domain of space-time, and this is how I usually want to demonstrate. In Draken's work, I have used a more technical version of this slide, which is next. But to put it very simply, all our theories of physics can be put on this cube called as the Bronstein cube after the person first used this in his papers. What is plotted it's a very cartoon picture where the fundamental constants, like Planck constant, Newton's gravitation, speed of light are plotted. And you can understand various theories of physics by putting the roles which H bar, G, and C play in their description at different points in this diagram. So quantum mechanics, for example, lies right here. It has H bar, but usually gravity is ignored there. Speed of light is also not there. So C going to infinity limit state. Then there is relativistic gravity. There is no quantum mechanics, but you're still trying to describe gravity in a special relativistic manner. It's not quite GR, but it's close to GR. It has more stuff in it than GR. And similarly, there is quantum field theory, non-relativistic quantum gravity. I would not want to indicate what that means. There is a formalism that existed long back. What we are focusing on, or what we are trying to lead towards, is quantum gravity, where all the fundamental constants play an important. But since we do not know the theory of quantum gravity, I would characterize as a mesoscopic domain space-time, a description of space-time that lies somewhere on this triangular region. It still has all the fundamental constants built into it, but still not quite quantum gravity. And we'll see where the inputs from quantum gravity would be required. But still a lot we can say without a full theory of quantum. It's a more technical version of the diagram, but I can come back to it if anyone is interested. So these are the various themes in which the research I am going to describe here. We are going to speak, like I said, about how clocks and rods, basically detectors, behave in a curved space, what information it can give us. We are going to talk about space-time at various scales. And I'm going to use detectors to probe space-time. That's the connection between the upper part of this. And the third thing we are going to connect all this up with is what I would like to call as space-time thermodynamics. And this is something I'll describe in the first part of the talk. The basic idea is that some insights from black holes tell you that black holes can have temperature if you treat them quantum mechanically. Stephen Hawking proved that black holes can be thought of as black bodies with some temperature. And then people realized that actually black holes are not needed. They are not the only objects which can have this thermal properties. If you have flat space-time, and if you are just accelerating in the flat space, uniform acceleration, then you can again prove that your detector or whatever objects you're carrying will behave as if they are immersed in a thermal bath temperature. So there seems to be some interplay between acceleration and curvature that we'll encounter again. One such, very first such. So black holes do not have much to do with thermodynamics. It seems that space-time itself, when it is probed by a certain class of observers, can behave as if it's a thermodynamic, as if it's an object with a temperature. Now you can do something more basic. You can look at the geometry of space and you can ask what is the entropy of, say, a hot cup of coffee if it is accelerating. Because I just told you that if any detector is accelerating in flat space-time, it will behave as if it has a temperature. If you already have a hot object, then how does the thermodynamic entropy that we all learn in thermodynamics of this hot object, how does that compare to this very strange entropy or temperature that I mentioned in any object moving on accelerated curve? It's an interplay here. Even if the object was at zero temperature, if you put it in an accelerated motion, it will behave as it is. The object is already hot. There's an interplay between statistical mechanics issue.
The thing is that when you're saying, so basically you need to confine the system into some system.
Yes.
Otherwise,
Yeah.
I won't be able to.
Yes.
Then, then thermal motion due to acceleration. I'm sure that
temperature
you will.
Yeah.
So, okay, I'll hear you.
Okay.
I'll ask the question after.
Yeah.
Because
but I'll probably anticipate slightly the spirit of the question.
Yeah.
And you need to confine the system. You probably need to consider, for example, this hot cup of coffee as a highly excited state of some quantum field. But this quantum field has to be a thermal field because you're already saying that this body has some temperature T. All I'm asking is how does its acceleration affect? We know it affects its temperature, it will. How does it affect entropy and all those things? And the usefulness of this will come to. So, in the beginning of the talk, I mentioned that there are two very important clues from studies in semi-classical gravity that we have had so far. And the two clues I have already mentioned, so I will just summarize it. That space-time can have thermal properties. I explain this in more detail as I have already mentioned that it comes from black hole thermodynamics. The second clue is that there is an operational limit on measurement of space-time intervals. And this can be demonstrated along the lines of how Heisenberg demonstrated his uncertainty principle. So whenever you hear about quantum mechanics, the first thing you hear about is the uncertainty principle. And if you have heard about Heisenberg's microscope, the way he tried to use to demonstrate the uncertainty principle is that just imagine looking at an electron using a microscope. What you are actually doing is looking at a light which is scattered by the electron coming into the microscope. And then quantum mechanics inherently puts some restriction on how accurately you can measure the position of the electron using such experiments. This setup is called as Heisenberg. Pretty basic setup. You can show that you cannot measure an electron to an accuracy which is better than h bar divided by uncertainty in its momentum. Delta x into delta p, uncertainties in measurement of position, times the uncertainty in the measurement of momentum is bounded by. There exists a somewhat very similar version of uncertainty principle when gravity comes in. But now it becomes more fundamental because it turns out that delta x, the uncertainty in measurement of position, can be uncorrelated from the uncertainty in measurement of momentum. It turns out to have a fundamental bound. That bound is given by Planck length, which is of the order of 10 to the power minus 23 centimeters. So in quantum mechanics, delta x is correlated to uncertainty in measurement of momentum. But if you bring gravity into picture, there is a fundamental uncertainty in the measurement of position, which is determined by Planck and all fundamental constants. There is no role of momentum. So these are the two insights I mentioned at the beginning, comes very robustly from semi-classical gravity. And almost all the approaches in quantum gravity that we know actually have these features in one way or the other. So it's pretty safe to take them as some basic features of combining quantum mechanics and virtual. So before I begin discussing this feature, I'll very quickly take you on a very quick tour of space-time and gravitation. So this will be familiar to all of you who have been working in GA, but just to set a notation and other things right. And for those of you who are not that familiar with general relativity, this should give you a very quick start. The fundamental insight of Einstein, which led to general relativity, is that gravitation is the geometry of space and time. That's why I've been mentioning space and time repeatedly. You make measurements using rods and clocks. You use a ruler to measure spatial intervals, clocks to measure time intervals. But the way these measurements stitch together also has an implication for a very fundamental force of gravity. That was the great insight of Einstein. And this essentially tells you how objects which have masses or energy content move. That was the content of general relativity. And the difference of general relativity from Newtonian theory, and this is something I'll come back to towards the end of the talk as well, is that instead of having a predefined notion of time or equal times hyper surfaces, so your definition of space is something that comprises all the points of the given instant of time. And the Newtonian picture of the universe was that you stack up all these three-dimensional spatial sizes and construct a space. So left-hand side is Newtonian space. But what Einstein's theory of special relativity plus general relativity tells us that no, you cannot do that because you cannot have information from events from which light cannot reach. And you cannot convey any information to events which you cannot communicate through a light signal. Light, the speed of light is an upper bound of all transfer of information. And that's why your description of the universe should be bounded by what is called as light. So although at present instant, Newtonian theory would have you describe all events for time and sequence, those are not accessible. The only accessible events you can affect which can are the ones counted. And the second aspect is, of course, the equivalence principle that everything falls under a gravitational field with the same acceleration. This we now know. We know the famous experiment of dropping a stone or other things. But essentially, uh, this is the thing which also separates gravity from other fundamental forces, because the fact that objects fall with the same acceleration under a gravitational field does not work. If you replace those objects by charges and put them, say, between the plates of parallel plate capacity, if they're falling in electric field, they will have different accelerations. And what this suggests is something that took almost 4 centuries to develop. This has been known since the time of Galileo. It just took a long time to recognize that this requires some kind of an explanation. And that is where Einstein's description of space is. The idea is that if something is universal in a gravitational field, maybe it's not property of some extra force, but it's a property of space and time itself. That's how we connected gravitational field, geometry of space. So the idea is that this fact is true. Everything falls with an acceleration of 9.8 meter per second square near the surface of the Earth. And that's when you are looking at it from a lab which is smaller. If you increase the size of your lab, then you will see deviations from this empirical fact. And that deviation is a measure of curvature. These guys will tend to fall at constant acceleration as long as you are measuring them in a small lab, but otherwise they tend to move towards the center of the Earth. And this much is true even in Newtonian theory. What Einstein added was that this is a generic feature of gravitational interactions. That if you look at objects in a sufficiently big region of space and time, then you will have an effect of space-time curvature, which is very similar to the effect of gravitation. And then there are formal, so I will not describe this, I've already mentioned this. So basically, the idea is gravitational force is equivalent to curvature of space. And then there are a lot of effects. I mean, these are the effects which exist in Newtonian theory but becomes drastic. And you consider relativistic effects. This is called as a tidal stretching. For example, the effect that causes tides can be understood in terms of curvature of space. And the basic equation of Einstein theory is that curvature of space-time is determined by energy movement of matter. And I will write that equation later. So just to give a very brief mathematical input. You take the Riemannian geometry, you take insights from Minkowski, and then you take the physical insights from Einstein. You get what are called as Einstein. Our basic picture of GR is that massive objects curve space-time produce this complicated object called as the Riemann curvature. And then other objects moving in the vicinity of this massive object follow what are called as special curves, geodesics, in this curve. So that is the summary of gravitational theory. And Einstein equations reduced to Newtonian equations. So that was my brief foray into quick description of GR. Now let me come back to the mesoscopic domain of space. So the two insights that I mentioned are the ones I want to discuss that order. Fact that there is an operational limit of measurement of space-time intervals and thermodynamic aspects of gravity in space. So let me begin with 0 point. And that's the thought experiment I was mentioning. One of the earliest ones, a beautiful paper by Salecker and Bailey. So very long back, this is 1957, they asked what would happen or how do clocks actually measure time? That is, if I want to say that some event in the universe happened at, say, 2 p.m. and I am having a clock, how do I actually assign time coordinates to events in space-time? The clock. The key insight which they introduced, and there is a quantum, is that if the clock is built out of A clock is a physical object. Physical objects properties are determined by quantum mechanics. The clock has to be treated quantum mechanically. Because it's treated quantum mechanically, there will always be an uncertainty in the position of the clock itself. That uncertainty will be induced into the uncertainty in assigning time to any event. So this is the clock trajectory. That's the event which we are trying to assign. The first line you can prove in any first course in quantum mechanics. That's essentially using Schrodinger equation to write uncertainty in the measurement positions. The second one is that you can assign time coordinate to events which are separated from the clock by a distance d, that d is the size of the clock. You're only assigning coordinates to events located outside where the clock is. And the final constraint is where gravity comes in. This is something I should explain. There are objects in general relativity which are called as black holes, from which nothing can escape. If you concentrate enough mass in a given region of space-time, you get a black hole from which even light cannot escape. Now, I also want my clock to not become a black hole, because then even if it can measure time, I'll never be able to get the readings of that clock. And that's this final constraint, that the size of the clock should be greater than what is called as event horizon. Clock should not be a black hole. If you combine these inequalities, you get this fundamental bound. And that is what I mentioned in the introductory slide. Quantum mechanics would tell you delta x into delta p, the uncertainty momentum, is bounded by h bar. Once gravity enters into the picture, it's a drastic modification. There's no momentum uncertainty here. Mass cancels out. So specific details of how massive the clock is gone. Size of the clock, t, is gone. What is left is a fundamental bound. And if you actually do this carefully, putting the speed of light, which I have set 1 and everything, you will get g h bar by c cube plus square per L. Because I've set h bar and c to 1, you can't see that, but that's easy to look at. So that is the clearest.
This is essentially saying the same thing that quantum wavelength is
Yeah, quantum wave, yes. But in the way you describe this, the quantum wavelength does not directly come, because this is just something that comes from the operator, the Heisenberg equation of motion for the position operators. So yes, but that is the condition also which gives you an. And then there have been a lot of work. This is just a slide where I put some references to convince you that the fact that there is fundamental limit on measurement of space is actually very robustly established by several mathematical arguments. And they have been put to good use as well, because if something is bounded from below, if I'm saying the measurement of distances is bounded, then it's a very good indicator of the fact that space-time itself will have quantum fluctuations. If you are not able to localize an event to an accuracy better than L naught, then this is a very, very strong indication of the fact that space-time itself may have quantum mechanical fluctuations, which is possible. Because the way you define distances is to use a space-time metric and then compute a proper time, a proper distance. So quantum mechanical space-time is a clear candidate which can cause such kind of fluctuations. That has been studied in several works. So basically the idea that we are going to push forward for is that you have, I will call it as a 0-point length of space. That is, even if you want to define distances between coincident events in space, those distances will be zero in standard theory of metric spaces. Quantum mechanically, those distances can be non-zero of the order of L. And I want to actually incorporate this to my description of space-time geometry, which at present is in terms of the metric and Riemann constant, all those things. The second fact, which I will not go too much into, but I hope to clarify it later, is that there are quantities which describe how particles propagate from one point to space-time in quantum mechanics. Classically, we know we just use Newton's laws and say how one thing is one point. Quantum mechanically, these are better described by what is called as a propagator, which is a function of the initial and final points. And for relativistic particles which are not being acted upon by any other force, the structure of this propagator is something like 1 by sigma square, where sigma square is the square of distance. So if I want a quantum particle to move from x to y, the amplitude or the amplitude or rather the probability of that happening in quantum mechanics is measured by the propagator. And one implication of a 0-point length is that this propagator gets modified from 1 over sigma square to 1 over sigma square. It helps you in a very important way because 1 over sigma square is singular when sigma goes to 0. So if I take the y going to x limit of the propagator, this is a well-known problem known for about 100 years now, that in quantum field theory, coincidence limit of such propagators are formally divergent. Yeah, and people have for a long time believed that if you incorporate quantum mechanics divergences, very similar to the way in which hydrogen atom, there is a divergence of the potential that the electron needs are equal to 0. In quantum electrodynamics, we are going to expect that it's regularized, which does happen. Something very similar, long history of this subject. So that was the first clue. And if there are any questions, we can come back to it later, because I want to combine these two. The second thing I want to discuss is the thermodynamic aspects of gravity and space. So let me go there. And like I mentioned, the original insight comes from black hole physics. So black holes are very well-known solutions of general relativity. These are objects which are characterized by basically 3 charges: the angular momentum, the mass, and electric charge event. And people figured out quite some time back that these objects seem to follow certain laws or certain equations which are very similar to the laws of thermodynamics. For example, the acceleration at the surface of these objects, as measured by an observer at any, is constant everywhere over the what is called as the event horizon of the black hole. That's the boundary of the black hole. That's very similar to the zeroth law of thermodynamics, which says that temperature is constant throughout the body. There is a first law, which is essentially the heat. Yeah.
Can I simply not say that the black hole is always a spherical topology?
In fact, the proof of this theorem does involve the topology of the event horizon.
Right, that's
Then there's an analog of first law, which is like TdS equal to dE plus PdV of your, basic thermodynamics. So the heat energy is equal to internal energy plus the work terms. But for black holes, this means something very interesting. Now, black holes are objects from which nothing can come out. So, and whereas this law will tell you that black holes have temperature inversely mass, they have entropy proportional to equal to 1/4 of the area. That factor can be fixed by some other. But if something has a temperature, you would expect it to be. But black holes are objects from which nothing can come out. There is a mismatch here, which is why Stephen Hawking initially very much objected to taking this analogy between black holes and thermodynamics as anything more than a formal mathematical analogy. But however, it was proved later by Hawking himself that if you do quantum field theory in a black hole background, then you get naturally something like a thermal effect, that is, a quantum field put in a black hole background behaves as if it was in thermal equilibrium at a temperature precisely given by 1/n. That's called as a Hawking temperature. You must correlate this fact with something I mentioned in the beginning, that accelerated detectors in a flat space-time look like black. A quantum field in a black hole that has thermal features. So it is somewhat similar. There are caveats. Those are for more. Those will call for more technical details. There's a second law which says that area of black holes always increases. If area is entropy, this makes perfect sense if you try to interpret it in a. So that's where the story starts from, and this is just the way people figured out why black holes actually have entropy in the real sense. It's not a fictitious mathematical object. But this entropy is as real as entropy of hot coffee. Because if you throw a hot cup of coffee into a black hole, entropy will be lost. Your third law will be violated unless black holes themselves have some entropy. So these are the laws of black hole mechanics, all proper constants between the temperature and the entropy of these. And again, try to hammer the fact that these are real quantities. You can actually do experiments along the lines of what Carnot did with Carnot engine. You know, when the heat engines were being understood during the Industrial Revolution, a lot of thought experiments involved transferring heat from a hotter object to a colder object, making it use work. This is how Carnot figured out. You can actually construct a heat engine. This is the Carnot. You can construct a heat engine with one end of it as the black hole. Now I'm claiming black holes at temperature. And you can have exactly a mechanical system mimicking a Carnot engine. You can take a box of gas, lower it very close to the black hole, pull it down. You can show something very interesting that this process has a Carnot efficiency which is determined by the temperature. Not very difficult calculations, but these are useful calculations to tell you that these are not fictitious quantities. You can maintain quantities exactly analogy to thermodynamics. Moving on, people then figured out that these are not something very much tied to black holes. We have accelerated observers in flat space, you can get the same. Now the temperature comes up acceleration. This time I put back H bar as something I mentioned in the first slide. There's also an entropy density that can be associated with surfaces that the observer cannot cross. These are called as horizons, local horizons. And that's also be 1 by LP square, you can forget. So this indicates that there is a fundamental link in the description of Einstein, that gravity is geometry of space, and a description of gravitational dynamics as thermodynamics, because black holes are solutions of G, and the solutions are behaving according to the laws of thermodynamics, which implies that gravitational dynamics might have a thermodynamic description. And this was then understood in a lot of technical details. What happens when the mass is across the horizon, mass disappearing across the horizon, how much entropy it will carry with itself as it falls across the horizon. Does this loss of entropy satisfy the laws of? And eventually the consensus was that you do have a one-to-one correspondence between the change of heat content as any object crosses the horizon. Even if the object is not hot, horizon is hot. You can put the horizon temperature here, compute TDS, which is essentially change in heat energy, and it can be related to the time. This is basically because all the approaches started from Ted Jacobson or by Parry and others, that Einstein equations are similar in status to the equations of the. So that is just I will put some references. And then the complementary view also works. If you try to compute, you go back to your cup of coffee, try to compute the curvature corrections to its entropy. They also have the form involving time component of Ricci, time-time component of Einstein. So the link between Einstein tensor and entropy becomes clearer in many different ways. I'll just do the time indicator. That gave rise to what is called as the emergent gravity paradox. That is, people then started believing that maybe gravity is not fundamental in the sense Einstein was trying to describe in terms of space-time. But maybe it has a more emergent description, a thermodynamic description coming out of some basic degrees of freedom. So that again is almost given us the basis. And when I talk about emergent gravity, there are actually many different ways in which we talk about either the equations of motion are emergent, or the action of gravity is emergent, or maybe space and time itself is. The last one which I want to connect with the first 0-point length of space time. I just want to hear about. So this is the gap which emergent gravity paradigm fills, the relation between thermodynamics associated with horizons and the equations of motion, Einstein equations. And I will not go through this, but this is a more formal way of doing all this. Just write Einstein equations on the horizon, show that they are equivalent. But that's not the only view. The second view is that gravity is also somewhat lower. You break down gravity Lagrangian surface bulk part, a part which lives only on the boundary of a region. Take any space-time region. It is a boundary and the volume enclosed within it. The boundary and the bulk part of these actions are related by this. That also can be given a thermodynamic interpretation, because we are saying that the degree of freedom in the interior of space boundary can be described in terms of degrees of freedom in boundary. And remember, the entropy that black holes taught us about was proportional to area, not volume. So this is yet another hint that gravity might be having a better description in terms of thermodynamics or statistical methods. And all these things generalize to what are called as Lovelock models of gravity, much beyond Einstein theory. I will not go into details of this Lovelock models of gravity, but all of them have the same features as Einstein theory, including holography. You can break this complicated Lagrangian containing many curvature terms into a surface and a bulk part, and you can again give the same thermodynamic interpretation. So that's for the emergent gravity paradigm. And finally, to rebuild space-time from all these clues, we want to put detectors. More detectors are behaving. Sunil, can I ask how much time?
Another 7 minutes or so.
Okay, so then I'll try to speed up. So let me start by description of a very basic effect which one observes when you put an accelerated probe in space, any curved or flat space time. These accelerated frames or accelerated probes are important because they connect up with a lot of fundamental principles in classical dynamics and gravitational dynamics, Mach principle. The basic idea is that anything you do in an accelerated frame, if the frame is small enough, can describe qualitatively at least the physics in a curved background, in a curved space. That was the reason for drawing the picture of a lab, which was very small, in which you see objects fall with constant acceleration. If the lab size increases, you will see the effects of curvature, but if it's small enough, the behavior of those falling apples and feathers and stones can very well capture the behavior of these same objects in a curved space. So that's the reason why we are interested in accelerated frames. And one effect that comes about with accelerated detectors, I've already mentioned to you, that they feel a temperature. And then, because they feel a temperature proportional to acceleration, you can ask, so forget about this, this is classical version of whatever I want to talk about, but because of the restricted time, I will not go into this. What you want to do is ask how this effect gets modified if the detectors are moving in curved space. So can moving quantum detectors measure space-time? Then what you find is that the result that temperature is produced by the acceleration gets modified by this. If you had a curved space-time, then this is something which is technically called as electric part of the Riemann principle. That corrects the new result in a very, very different. It's not a Taylor series expansion around the flat. It's sort of what you would have called as a non-perturbative square root of a square minus. And the way this result comes about is a very remarkable resummation of finite series, which is otherwise not possible just by staring at the perturbative terms, term by term, in a given expression. It is something like trying to figure out periodicity of sine of x by looking at its power series expansion near x equal to 0. That cannot be done. You encounter the same issue. So basically what we learn from this is that even locally, you don't need to have extended detectors. The detectors can have information about curvature of space. That's my first hint. My second hint that curvature can be embedded into the responsive detector comes by looking at uncertainty principle. I have mentioned uncertainty principle several times, but actually you can do much more formally with uncertainty principle by trying to formulate it on any curve, Riemannian or Lorentzian value. Something I'm not going to describe in detail, but I will just mention the final results. So here is a description of uncertainty principle in a slightly mathematical term in terms of commutators of position and momentum operators. You want to ask how it gets deformed. That is something usually done, how it gets deformed background curvature. And that can actually remarkably be worked out. I'm not going to go through any of these mathematical details. I just write to the final result, which is essentially this. So the commutator gets replaced by this object, xp commutator, and that object is determined by the extrinsic curvature of surfaces formed by sending geodesics of constant size lambda. And this is the tangent to the geodesic connecting the point x0 to a point x. This can be in the position space or in the momentum space. If there are any questions, I'll describe the relevance of each of these terms. But basically, we have a handle on how uncertainty is in curve space. In flat space, you can show that this combination is a conical delta, so you cover Heisenberg's equation. In curve space, and that you can use to work out how the deformation will look like in the curved momentum space of special relativity. Still no background curvature. Even if your momentum space, that space-time is curved, that will leave its influence. So that was my second reference to how curvature of space-time, but this time it was not of space-time, it was of momentum space. Any kind of curvature can actually affect your measurement processes and probes and how they respond. And in the final few minutes, I'll try to put all of this together to see what they imply for a quantum space. So now, what we are going to do is use all these insights, thermal aspects of price space, and ask is metric tensor the right candidate for describing space-time at a quantum level. And this was already envisaged. I usually do display this quote by Riemann from his famous lecture. I've not spent time on this, but he already envisaged that his setup of Riemannian, what we now call as Riemannian geometry, already in a domain of very small, should refer to science other than just pure mathematics. We should have to input some physical arguments to know whether it's a valid description of physical universe. So what we do is take the geodesic distance between 2 points of the fundamental object and try to reconstruct the metric. But eventually we want to do it for the case where the distances can never go to 0. Even if 2 points are sitting on top of each other, we want to have a description where the distance measured is still non-zero and given by Planck. That's what so far I hope I have tried to convince you happens in the real quantum space. And that gives you a very nice description. Because almost all our observations, like redshift, Doppler effect, all those things, can be described in terms of this geodesic distances between events. Technically, it's called as the Singe world function that measures these intervals. And what we are saying is that can I shift focus from this? This goes back to my older figure, how Einstein described curvature of space-time and gravity as a We now describe it in terms of distances. If you do that and follow through the math by imposing all our proofs from 0 point length of space-time, you can derive a complicated object, which I call as a quantum vector. That does the job for you. It describes a space-time at a 0 point length. But more importantly, what it does is that when you take the Einstein-Hilbert action, the gravity action constructed from this one point, and take its local limit, it leaves a relic. We in our first paper on this, Paddy called it as a grain of this shaft cap. We already removed this phrase from the package. Yeah, but it's something like that, because what you are left with is not Einstein-Hilbert, but rather precisely the entropy density which we encountered earlier in the emergent gravity. And that connects the relic of a quantum space with the emergent description of space. This is quite an unexpected result, but it actually was the first proof of why the emergent gravity paradigm provides a better action principle than yeah.
Basically, this additional term
Yes.
came as the entropy. Now, can I?
So that is the entropy density, yes.
Can I expect this on a physical ground that is,
So far, we have not been able to give. Yeah, that would be desirable, yes. And we have some results from Euclidean gravity which suggest the same thing. Like you pointed out in Drakensberg, combining these two could give an interpretation of this. Because action itself is rather interpreted as free energy, not the entropy. So that is the summary. So the new description would work just with the singular function, distance functions. And leave you with, there are other relics as well, but I think there is no time to discuss all of them. The only thing I will discuss is the dimensional reduction. But one thing which I mentioned but not displayed in Drakensberg, so for those of the audience who are common in the two, light cones seem to close up in the quantum space-time. So these are the Minkowski light cones, but as you go to a distance of the order of Planck length, these light cones seem to close up. That we have tried to connect it up with the phenomena called as asymptotic silence. Yes. It also has implications for singularity theorems, which I will not discuss, the so-called BGV theorem. And it also has implications for measurement of redshifts. Now I can almost upgrade my basic Doppler or gravitational redshift without space-time by incorporating quantum mechanical features of space-time. So that is one thing that we are presently trying to do. That will be the observable effects of what we are calling as a dream.
So you're working on
This thing is worked out.
because I feel that it will be too small.
It is. These are too small. Yes. These are too small. So what
With
we
the present.
yes. Although some people there's a collaborator in Italy who, along with Sumanto, have tried to work out a measure for this, which can leave imprints in gravitational wave observations.
Yeah,
I am very skeptical, and so that's why I have not described it. Yes. So this is basically the summary of the talk. This is the part I have not discussed, but I just briefly mentioned to response to this question. So small scale structure of space-time plus the thermodynamic features of horizons in space-time can actually give clues to the small scale structure of space-time. They are strengthened from other directions as well, which I have not discussed. But I hope I have conveyed basic message. So I think this is it.
Here, they can talk. We have time for one or two questions.
The geodesic that you took as instead of So to define the space-time.
Yeah.
So,
Yeah.
but how do you measure? How do you measure the isn't it that you are doing? So you are taking as a this thing. You
Yes,
are taking a
yes,
space
yes.
and then you are seeing
It's so to begin with, it's not in a curved space time. That's the so to begin with, it's not in a curved space time. But maybe those identities I have. So what happens, Shubhat, is that if you take this distance functions, so this is the object and square object of the distance. The known properties of this object is that you keep taking derivatives of this square.
Oh, okay.
And this will give me the metric. This will give me something like V1 tensor. If you take appropriate, this is a very sketchy way of writing it.
I got that.
The idea is to rebuild curvature and everything from
The physical solution for that your light forms contract in when you go.
no, there's no physics explanations.
Okay, why doesn't I say other way around? Why don't you explain?
Well, that has to do with actually the fact that I have drawn the light waves. So at that question, one can briefly address that these are all light modes lying within the Minkowski light mode settled constructed on this. I have drawn the light modes here, which means they would have expanded. But I only want to construct a causal
Further thing. So
domain
that
corresponding to this. But yeah, you can go further.
one would generally believe that your light will be fuzzy.
Yes. So you are saying that it could go in both the directions.
So then you are at that limit.
Yeah.
With that level.
Yeah. But here, as long as you are in this one.
Student? This is the low level. You speak in the relativistic approach also, you also find the best theory is now to do bypass. One has to argue whether it's I think there have been the belief is that the extra dimension largely multiplied as a experience scale. The belief is that they are extra dimensions.
Yeah, there are more here.
Something that I talk about Steve Morgan. He spoke about quantum. So,
Yeah, quantum black holes is what you would call black holes with Hawking radiation and back reaction put in. Yeah.
your thesis is all four dimensions.
Yes. But I mean, as long as the basic idea is concerned, it can be extended to higher dimensions. Right now, that's not required by any of the, I mean, 4 dimension is not required by anything in the formalism. The only place where dimensions play a role is dimensional reduction. But even here, you start with 4 and we see that some effective dimension goes down to 2. But one could have started with n dimensions.
I thought the quantum theory you need dimensions.
No, quantum theory by itself would not require higher dimensions. Quantum theory would not.
String theory.
Oh, string, yeah, string theory may require. Yeah. But this has actually nothing to do with string theory as such. Yeah. That's why this mesoscopic domain I was very specific about. Some features of this do match with what comes out of string theory, but the formalism. So I should mention here that at least a few people have tried to connect a description based on the world function with identifying the 2 points x and y appearing there as points of an open string. Okay, this is Bailak, Ho, and Rice, but these are all just comments stated in a paper, not been made more mathematically. Yes, last question.
Can you comment on the principle of equivalence?
Yeah.
What is the status of that? Very good.
So here, I can only say that Lorentz invariance is what we have kept intact, but the principle of equivalence is extremely murky. Like which principle of equivalence we are talking about. And in fact, one aspect of it, just before the talk, we and Naresh were discussing because of the paper which appeared. Okay, but there are various levels at which principle of equivalence can be discussed. Here, if you're talking of strong equivalence principle, I actually have nothing more to add. The quantum space-time will not do much. It will not break it. But then some people believe that even the existing higher curvature theories can break the principle of equivalence, interpret it in different way. Yeah, so we can talk about this more, but for a quantum space-time, I don't see anything which is different from the classical.
Good last question. In that case, let's thank the speaker again.